Hi everyone. I am happy to, I guess, meet you today. As Mario said, my name's Madhav. I am a second year computer engineering student at the University of Waterloo, where I've been very excited to learn about how we can try and make AI work for the good of us all, try and deal with some of the issues that come up so that it can be reliable, get done the cool applications that get us all excited. Um, I actually started learning about math when I was kind of around your age, when I was in grade 10, which seems like a long time ago now because I'm getting older. But when I started learning, it seemed very confusing to me. Just so many, stacks and layers upon layers of concepts, linear algebra, calculus, all these things that I didn't know about, that I was confused to learn about. That's kind of why once I dragged myself through all that misery, once I was able to figure it out for myself, I wanted to create some easier resources for other young people like me so that they can, skip the hassle and figure out what it is that they need to figure out. Um, when I last did this, I created a course on YouTube, like a 12, 20 video course, and now I guess I've been challenged to distill that down into 1 hour, which is going to be a challenge. So what we're going to do is I will show you the math of how the simplest AI algorithms work, talking about the key categories of algorithms involved. I won't uh, I won't be able to explain to you, how something like ChatGPT works, but I'll show you how one of the 175 billion building blocks that go into ChatGPT, how they work. Just before we get started here, I'm going to quickly ask you guys, I just want to know how simply to try and explain the math. Um, if you wouldn't mind, could you leave what grade you're in the chat? And in the meantime, I'll just show you the three categories of content that we'll talk about while you're doing that. So I'll first introduce you to the kinds of AI algorithms that exist and some of the math notation that you'll need to get used to understand how they work. Then I'll show you how an AI model goes about generating a prediction, giving us an answer to the question that we asked it, and how we can figure out how well it's doing, or maybe, how much error it has. Finally, I'll talk about how we can improve the performance of AI algorithms over time, how we can teach them to better do the tasks that we assign them. At the end, I have a demo for you, which I hope will be fun. I tried to minimize the code and increase the pictures so that you can see some of the results. And throughout, we'll be asking questions, so if you have something for me, feel free to let me know. Just to check the chat before I get started. Okay, good. So what I'm going to do is I'm going to try and explain everything at a grade 8 level. If you're in grade 7, I hope you're ready for a challenge, I guess. Just let me know if you're not understanding something. Feel free to type in the chat and I'd be happy to explain. So to get started, we're going to talk about the first category over here, which has to do with the kinds of AI algorithms that exist and some of the notation that you need to get to know. So when we talk about AI, artificial intelligence, the key thing to note is that this is a really, really broad term, and people have been creating algorithms for maybe 80 years, at least 60 years, that could fit into artificial intelligence. What we're basically talking about is a whole bunch of algorithms that figure out how to solve a task without a human like me or you specifically writing, here's step one, do this. Here's step two, do that. We want the AI algorithm to figure out the steps itself. The two main ways that AI algorithms can do this kind of thing, there are some methods which are very much like a parent teaching some kid, how your parents taught you how to ride a bike or how to read or write. We have what are called supervised methods. So for example, let's say anyone was teaching a baby, what is this animal at the zoo? What is that animal? They would let the baby to see a picture of, let's say, a cat, and then they would be like, hey, say a cat, or a house, say house, or whatever. Just showing the baby, here's an example of the thing, and here's what that thing is called. So this is how a human, I guess, would supervise another human. A parent would teach a child. But in our case, it's going to be a human supervising an AI algorithm. So we're going to give it some kinds of inputs, and we're going to give it outputs or labels, where we just want to give it lots of different examples of the inputs. So in this case, these inputs are images, and we want to give it lots of different labels. So we might give it, 1,000 cat pictures and hope that it recognizes by itself, here's what a cat looks like, without a programmer needing to write, here are the 100 steps instructions for how to recognize cats. Of course, I've just drawn the inputs as images here. They don't need to be images. For example, when you're using ChatGPT, you're not putting in images as inputs, you're putting in sentences. Or if you're using Siri, you're not doing either of those things. You're speaking to Siri and it recognizes the audio as input. So the general idea is show it the input data and then tell it what do you want this to be recognized as. Let it figure out all the stuff in the middle by itself. The other category of AI algorithms is what are called unsupervised AI algorithms. So instead of, here's the input, say cat, say house, whatever, with unsupervised algorithms, we basically just give AI algorithms a bunch of data, and then we ask it, do you see any patterns? So maybe the AI algorithm goes, yeah, it looks like here's a scatter plot, and there's a bunch of data over here. We can group that together. There's some data over here, and maybe this thing is an outlier. There's some data over here. This kind of stuff, it gets a lot harder. It's actually what ChatGPT, those complicated models, it's actually what those are trained on. So for today, we're just going to avoid this. It's too hard for us. We're going to focus on these kinds of models, supervised models, which are a lot more common and easier to understand. So before we move on, again, recap, these are the kinds of AI algorithms. I see we have one question in the chat. If you have any other questions, feel free to go on the mic or let me know before we move on. Okay, another person, grade 8. Anyone have any questions about the kinds of AI algorithms before I move on into some notation about how supervised AI algorithms work in particular? All right. I'm assuming that there are no questions about this, so I'll move on to the next section on the notation behind AI algorithms. So as we try and get into the notation, I just want to do some math background, especially for the students in grade 7. And just to answer the one thing for Stephen. So supervised is the kind of AI algorithm. It's the kind of AI algorithm where we show the algorithm lots of examples of some input data and give it some output labels. So, this is a cat, this is a house, etc. We try and let it figure out how to recognize, okay, images like this look like a cat and images like this look like a house. It's not yet a function. We're now going to get to define the kinds of functions we need to create these algorithms. First off, though, for especially the grade 7 students and grade 8 students, just a recap of what actually is a function. I hope that some of you may have seen equations like the one at the bottom here, y equals 2x plus 3, where, well, some of you, if you're in higher grades, you might recognize, oh, this is the equation of a line. But in general, all we need to know is that this equation has some numbers and variables, and we can take the variable x, let's say it's equal to 2 or 5 or 10, whatever. We can put it into this equation, and then we'll have something like, okay, let's say x is equal to 2. Then we put it into this equation, we get 2 times 2 plus 3, and that's going to give us 7. So we can take our input variable, x, put it into this equation right here, and then we'll get back some output, which we call y. So an equation for us, it's really just a way of relating two numbers where these highlighted things, the orange 2 or the 3, those could change. So for example, I could have another equation. It could be like y is equal to 5x, and there is nothing after it. That's just on its own. That's a possible equation. You could have fractions in there, you could have decimals, anything you want. Uh, all of these things are just showing us the relationship between the input variable and the output. Another math notation for this is function notation. Function notation is very useful in computer science because basically all of the code we write, we like to organize it into things called functions, which do the exact same thing. They just take in some input variable, modify it around, and then that results in the output. So these two things, they're just notational differences. They say the same exact thing. They tell us the relationship between this input and this output. Just one thing to notice, the reason that this notation, f parenthesis x, is written like this, you have the inputs to the equation put in the middle of these parentheses, and you read this as f of x. Anyone have any questions about function notation, especially the grade 7 students here? Okay. If not, just a concept that maybe you guys haven't seen, just extending this further. Here you see we have equations relating the input variable to the output, and these equations just have one variable. It doesn't need to be like that. We could have as many variables as we want. So here's another equation, z is equal to 4y plus 3x plus 5. Maybe this looks a little bit unfamiliar. You're used to putting y over here, but it doesn't matter. We're still saying the same thing. We're just trying to describe what is the relationship between these inputs and this output. Again, we could use function notation here. You'll see that in our function notation now we have two things in the middle of the parentheses, just because the equation, it depends on two variables, y and x, not just x. The last thing I'll just note is that in computer science, we often will rename these variables. We might not use, different letters. We might just add subscripts, so like x1, x2. It doesn't matter. They're just different names for variables. We can name the variables whatever we want. So if you have any questions about this notation in particular, let me know, because we're going to be using it for the rest of the lesson. So now that we have function notation, this is the notation we'll be using to describe inputs versus outputs. You can see how this kind of thing might be useful for the problem we just set up here. We have some inputs, we have some outputs. We're going to create some kinds of equations that can relate these inputs to these outputs. In particular, let me walk you through an actual example, a real-world example. So in BC, in Ontario, really in all of Canada, you have energy companies that are trying to get you electricity. They have to do planning because they have to build power plants that take maybe 5 years to construct. So they need to figure out, which things do we start constructing now? What do we invest in so that we can keep meeting electricity demands everywhere? So let's say that you have an energy company in BC. They want to figure out, we want to build a new natural gas plants, and we have some, offer on the table. But we need to make sure that the natural gas plant that we're considering, we need to make sure that it doesn't emit too much CO2 so that it meets the regulations we need to meet. So can we create an AI model that will help us predict, how much CO2 will this particular plant, this new plant that we haven't yet built, that we just have plans for, how much would it emit once it were built? So this is a prediction task. We're trying to predict something that's going to happen in the future. And how do people usually make predictions? Well, they look at what's been happening in the past and then use that data to figure out, to predict what might happen in the future. So if I were an energy company in BC, I probably own existing plants, and I probably have data about some of the technical characteristics of these plants and how much CO2 that they emit. So let's say that we know for 10,000 existing plants that we have, how much electricity they produce in kilowatt hours. That's just an amount of electricity. We know how efficient the plants are. So if if I burn 10 kilowatt hours of fuel, how many kilowatt hours of energy, electricity do I get out? This is going to be a percentage value. So if, a plant is 100% efficient, all of the energy we send into the plant, it gets converted into useful electricity. If it's like 1% efficient, then most of the energy is being wasted. We're not getting very much electricity even after all of the energy we put in. The last thing we know about these plants is whether they have carbon scrubbers installed. These are just devices that remove CO2 from the air. So just preventing the CO2 from reaching the atmosphere. So making sure that there's not too much CO2 being emitted. Finally, for each of these 10,000 plants, we know how much CO2 they emit because they're plants that we already own. They're out there in the world. We don't need to make a prediction about them. One useful thing that I'll do for this data is I'll note that these variables, they are the information, the useful information we have about plants that is related to CO2 emissions. But this is the really useful thing. CO2 emissions, that's the output we want. That's the thing that we want our algorithm to generate predictions on. So because we're using supervised algorithms, we have to give it some inputs with which to make the output prediction. What we can do is we can make all these variables our inputs, give this data to the AI algorithm, and then try and teach the AI algorithm to predict the output. So use this information to figure out how much CO2 would a power plant emit. So some notation that I'll introduce here. We want to set up some equations that eventually give us predictions about this output. Since this is very special, I will call this output y, because we often call the output y that we're trying to get out. Well, that's what you're used to anyways from these equations. So let's call this output y, the thing that we're trying to get out, the CO2 emitted. And I will make an important distinction here. So we have some existing data that we know what is the CO2 emission level of all these existing power plants, and we have the predictions we generate. So an AI might say, okay, I have a coal power plant that generates like 10 tons of CO2 emissions, and that's not very accurate. It could be that Y, the predicted CO2 is very off. But luckily, we know what the actual CO2 levels are. So that's why without this little arrow on top, so that's the known CO2 for these plants. We know how much they emit. This thing, it's read as Y hat. This symbol is called a caret, but I'm just going to say Y hat from now on. So we want to generate predictions with the AI algorithm. So that's going to be Y hat. That's what we want to get as the output. To do that, we have some useful inputs over here. So these inputs, just like the notation I showed you over here, we're just going to label them X1, X2, and so on. So this can be X1, this can be X2. By the way, I don't think I mentioned earlier, the carbon scrubbers, these are going to be ones and zeros. That's what I've written here, 1 or a 0. So, if you have one carbon scrubber installed, you get a 1. If you have none installed, then you get a 0. So I want to create an equation that uses these inputs somehow to generate this output. Okay. I don't want it to be a very complicated equation. So I'm gonna base it off of these equations over here. Except, I have 3 inputs, not just 1 or 2. So let me just write 3 things. So I have x1, x2, x3. I'm gonna multiply them by various numbers, just like those equations on the left. So let's say like it's 4x1 plus 2x2 plus 9x3. Add in our plus signs. And we can even have an extra number over here. So let's say plus 6. Why not? Now this is a perfectly valid equation to go from our inputs to the predicted output we wanted. But, you'll probably be thinking like, why that equation in particular? How do you know that it is exactly 4x1 plus 2x2 plus 9x3 that will help us predict this output that we want? In particular, the question we have is, these numbers, they seem very random. How do you know that these numbers are what we should use? And that is actually the question that the AI model has to answer. Which numbers do we put in here? Which numbers would help us best take the input data, combine it in some way that lets us get the output we desire? I see some questions popping up. Yeah, so someone is saying replace 4 with A and 2 with B. You're treating the numbers like variables, and that's essentially what they are. So we have to figure out, not we, the AI algorithm has to figure out for us which numbers to put in here. So for the AI algorithm, its job is basically to generate a bunch of equations like these, which we will call prediction equations, because they generate the predicted variable we want. But it has to change these numbers. It has to make lots of different guesses at what these numbers are that would best allow us to make the predictions. So these things, these numbers, these are called parameters. Just like the French word paramètre, which means settings. These are just settings of the AI algorithm. It has to adjust these settings, adjust these dials and knobs to figure out how best to achieve the goal that we gave it, which is to predict the CO2 emitted by these power plants. So this is a key equation that we'll be using going forward. Anyone have any questions about this equation before we talk about how do we figure out how wrong the AI algorithm is? How do we help the AI algorithm make better choices for these numbers or parameters? So while you're typing out your questions, if you have any, we have finish this part, and this is the part that I'm talking about. We just created the kinds of equations that AI algorithms use to generate predictions, to give us the answers we're looking for. They create equations like these, but their job is to adjust these parameters or settings, which are the numbers that the AI algorithm plugs in. It has to choose the best numbers for the job. So if there are no other questions, keep this equation in mind. This is the way that an AI algorithm gives us its predictions. It creates math equations like these. Surprising result, I know. So now let's move on to the next part, which is we have to figure out how wrong or right is an equation that the AI algorithm gives us. Has it given us good parameters? Has it chosen good numbers that predict the answers we want very well? So if it has done this, then the error of the AI algorithm is going to be low. It's doing the job well. If it hasn't done it, it's going to be high. It has a high error because it's not chosen good parameters. It's predicting very random CO2 values. So to measure the error of an AI algorithm, we need to create an error function. We need to create another math equation that will tell us, has our AI algorithm done a good job or not? Can we start using it in the real world? So just like your math teachers, when they're trying to figure out are you doing a good job of learning, we have to create some tests. But these aren't tests for you to do in class. These are tests for the AI algorithms. We have to create a test that the AI algorithm will do so that we can figure out, is it doing a good job? Has it chosen the right parameters yet? Can we start using it? And if you think about, what a ideal test would be, well, we have the AI algorithm predicting CO2 values. We know what the proper CO2 value should be for these 10,000 plants. We just have to compare, are these two the same? Because if they are the same, then the AI algorithm is doing a good job. If they're not, then the AI algorithm isn't predicting what we want. So let's say that we're talking about the very first of the 10,000 power plants that we know about. So we have 10,000 plants. The very first of them that we know about, we will label it Y1. This weird notation, it just means this is the first power plant. It's not like a exponent, it's just notation. So let's say the very first power plant is generating 10,000 tons of CO2 emissions. And we get back, let's say, the predicted value from the algorithm, again, for the first power plant, not an exponent, just means first. Let's say the predicted value is like 4,000 tons. Well, if we get this, then we know the AI algorithm isn't doing its job well. It's supposed to predict 10,000, but it's only giving us 4,000. How much error is there here? Well, we can just take the difference between these two to figure out the error. So we know that it's supposed to be 10,000, subtract away what it actually gave us, which is 4,000, and then you'll get like a difference of 6,000. That's the error. One of the issues is, okay, let's say that it didn't predict 4,000, it actually predicted 14,000. Now, if we try and measure error this way, then we're going to get 10,000 minus 14,000, you're going to get negative 4,000. And it's kind of weird because like now you have a negative sign. Before, when this was 4,000, you didn't have a negative sign. So how do you compare these two things when they have different signs? How do you compare these numbers? It turns out we kind of don't care if the sign is negative or positive. It's not very useful information to us because we don't care if the AI algorithm underestimated this value. We don't care if it overestimated this value. We just want to know, is it right or not? So we kind of want to get rid of this negative sign. If it's there, just like positive numbers. It's simpler, it's easier for us to make decisions with. There are different ways that we could make sure that, this difference is always positive. A common way to do it is we could just square whatever this number is. So if we multiply this by itself 2 times, so raise it to the power of 2, if we do that, then remember, if you have two negatives multiplied, then the answer will be positive. If you have two positives multiplied, then the answer is still positive. And because of that, now it's simpler for us to interpret, what does this result mean? Because we just get back a number that doesn't have signs for us to worry about. It just tells us if number big, AI algorithm bad, if number small, AI algorithm good, and that's the way we like it. It's very simple. The issue is, well, just like, if you devised a test, if your teacher gave you a test that just had one question on it, then it would be very easy for you to cheat or memorize the question. If we just measure the error on this first power plant, well, we're not getting back very useful information. We want to figure out what the error is across all of the 10,000 power plants that we have data for. So to do that, well, you can imagine what we're going to do. We're going to just add together the error across all examples. This is going to take a while for me to write out, but I will give it an effort. Bunch of additions. And if you think I'm going to write out 10,000 of these, then you are wrong. I will show you some mathematical notation soon that will simplify our lives, but let's give it an effort. So we're doing it for the first example. We're doing it for the second power plants, the second example, third power plant, third example, all the way up to I didn't give myself enough room here, all the way up to the 10,000th power plants and the 10,000th example. Because this is very annoying to write out, mathematicians have a shorthand notation for this. So this big long sum of just terms like this for every single power plant that we know about, from like the first one to the 10,000, we can write this big long sum in this thing called sigma notation. Means the exact same thing. Again, just notational difference, just like this f of x notation and y, these are just notational differences that mean the same thing. We can write a shorthand that is the same. The shorthand is this Greek symbol called capital sigma. I will write an I, which is just a variable, just like, y is a variable, y hat is a variable. I starts at 1, and I goes up to 10,000. And we take I and we substitute it into these terms. So let me finish writing this out and then I'll explain. Yeah, messy. So this compact expression, it means the exact same thing as this thing above. So these two things are the same. This is just mathematical shortcut notation that's common in computer science. What it means is, you see this expression over here, it is basically like an equation. We take I, a variable, plug it into the equation, and then we'll get back a number. So for example, when I is 1, then you plug in 1 and 1 here. So then you have y at 1 minus y hat at 1. Well, we can see that y at 1 is 10,000, y hat at 1 is 14,000. So then 10,000 minus 14,000, that gives you negative 4,000. You square that, you get 16 with a bunch of zeros, and then you move on to the next one. So then you move on to I is equal to 2 and I is equal to 3. Figure out what all of these values are, and then add them together. This is called summation notation, just a shortcut so that we don't have to write out this very big, long, ugly sum. Does it go up to 1,000 or 10,000? Yes, you're right. It should be 10,000. Thank you. So it goes up to 10,000. Anyone have any questions about this? Just this alternative notation so that we don't have to write out this big, ugly sum? If not, just one last thing to note is that this is a very, very, very big number. Like I said earlier, even if you just do it for, the first example, you get like 16 with a lot of zeros. If you're adding together 10,000 very big numbers, you get an enormous number. We don't want that. So what we can do is we still want like some interpretation of how large the error is across all of the examples. So, well, if you recall, if you have like, a bunch of numbers that you're adding together, 2 plus 4 plus 5 plus 8, and you want to figure out, how big are these numbers in general? Well, what you can do is you can take the average of these numbers. So to take the average of 4 numbers, you just add together the 4 numbers, divide by 4. To take the average of 5 numbers, add together the 5 numbers, divide by 5. To take the average of 10,000 numbers, here we're adding together the 10,000 numbers, and then we're going to divide by 10,000. I need space. Okay. We're going to divide by 10,000. 1, 2, there we go. So this is our final error function. This is what we call mean square error. Mean because it's kind of like we're taking an average. We're adding together a bunch of numbers, then dividing by, 10,000 in this case, because we're adding up 10,000 numbers. So this part is the mean. You can see here, this is a square. And this is what we call an error function. If we get back a very large number here, it tells us the AI model is very wrong. If we get back a small number, the AI model is better. Does anyone have any questions about this error function or how we can use it to check, is this equation that we've selected, is it very good or very bad? So again, if we choose a very bad set of parameters over here, these parameters are just giving us values like, 0.3 or 10. Well, we're emitting like tens of thousands of tons of CO2. We know that can't be very accurate. So this expression, if we've chosen bad sets of parameters, it will give us a very, very big number. So it is our error function. It allows us to test. Are the parameters that the AI model has chosen, are they good or bad? So now what we have is we're almost done. We figured out the kinds of algorithms that exist in AI. I showed you how they generate predictions. They just generate equations like these. And we can check if the equations generated are good or bad with this error function. So now we just have one last piece of the puzzle, which is actually the most important piece of the puzzle. How does the AI algorithm optimize these parameters? i.e., how does it take, my random parameters that I just threw in, like 4, 2, 9, 6, just randomly chose them on my head. How does it go from these to parameters that actually work well, that do the job well? How does it figure that out? This is the critical part of AI. This is the part where an AI algorithm will learn by itself to do the task that we have assigned it. We won't give it like step-by-step instructions to choose the parameters. It will figure it out by itself using the algorithm that I'm about to show you, which is called an optimization algorithm because it optimizes the parameters. Anyways, the algorithm I'm about to show you. So like I said, we have a question. Are these good parameters? Are these random numbers some good parameters to use? And ideally, are they the optimal? Are they the best parameters that we could choose? There is just a little asterisk. Right now, I have like three variables. In real AI problems, like more like hundreds, thousands, tens of thousands of variables on this side of the equation. So, you could keep extending like plus x4 plus x5 plus x6 plus x 9861. When we have so many variables, it's really hard to like figure out what are all the possible numbers that I could choose, the parameters that I could choose to put into this equation. So we basically never find the best choice in any optimization algorithm in AI. It's almost always the best choice that we can find. There's a fine print. It's just good enough. It's maybe not the best choice for these parameters, but it gets the job done. So that's what we want to create an algorithm to do. Just as a preview, before I show you the steps of the algorithm, we already have a lot of inspiration from biology when trying to create algorithms like this. When we say artificial intelligence, even at the start, I gave you the analogy of how a baby learns. The parent shows it a cat, say cat, the baby says cat eventually, then it can say dog, then eventually it turns into us, people that can speak, that have language. So biology is very good at learning new things. And the process that it uses to learn new things, we can copy and make algorithms out of, which I think is really fascinating. I find this really cool that computer scientists are like, okay, how does biology do it? We'll just copy them. And then, as humans, we get more useful things out of it. So the way that biology generally optimizes things, if you think about, genetics, we all have DNA. The DNA is, the instructions for how our body does something. Sometimes the DNA will have random mutations. It used to say one thing and then randomly, it changes. When this thing happens, well, that's how all of life is built up, just random trial and error. Are these genes good? Are those genes good? If you have a mutation that helps you, then you'll be better at surviving. If you have a mutation that doesn't help you, then you're going to be more likely to die. So we're going to recreate that evolutionary algorithm, that genetic algorithm that biology uses, just trying things randomly, and then the things that don't work well, those die, and you have survival of the fittest. The things that do work well will keep around. So in particular, um, I will show you the steps of the algorithm. You'll see how it's related to what I just outlined. So this is called a genetic optimization algorithm. Fancy words. It just means trial and error. What we're going to do is we're going to generate a bunch of very random prediction equations. So a bunch of equations that look like this one, where we just change the numbers, the parameters. So this 3, it could be like a 0.89. This 4 could be like 10 million, whatever. We're just going to randomly pick numbers to assign, and we'll create like, let's say 100 equations like these. For each equation, we're going to check the error that the equation has. This is like how well, a mutation helps you survive or not. If you get a really high error, then we chose equations well. The randomness, it helped us. If we get a very, no, opposite. So if you get a very high error, then you didn't choose well. The randomness does not help you. If you get a low error, then your, randomness helped you. You chose you trialed and errored your way into a good solution. After we know for, let's say all 100 equations, what is the error? Some are doing very well. They have low errors. Some are doing very badly. They have high errors. We're going to update each equation. So this is like our random mutations coming in. So the equations that are doing worse, they have a very high error. We're going to update them more. So like, let's say this equation it was doing very poorly. Then we might say, okay, this 3, we need to really, really change it. This is not working at all. Let's like add 1,000 to it. But if it turned out that this equation was working very well, well, we might not change the 3 very much. We might add like 0.1 to it. So that's what I mean by the equations that are performing best, they get more updates, that they get less updates. The equations that are really, really wrong, they get more updates. Also, just like biology, we're just going to delete like the n worst equations. So let's say like 5 worst equations or 10 worst equations. We're just going to replace them. So those equations, they died out. It was not survival of the fittest. Those were not performing well enough. Their error was too high. So we just got rid of them and we're going to generate some new equations to take their place. So that's like in biology, some organism, its mutations don't help it, so it dies out. I have a demo to show you to show this algorithm working, but anyone have any questions before we end off this theory and actually look at some results? Okay, so let's move on to some results. Just don't panic about the code. You don't need to understand the code. Just wait for me to click things and eventually pretty pictures will appear. So yeah, don't worry about the code. Um, what I'm going to do while I'm waiting for that to load, what I'm going to do is because, as I mentioned earlier, usually in AI, you don't have 3 variables, you have like hundreds or thousands. I have to generate a data set of my own to make an AI algorithm run on, because I wouldn't find a data set out there that, would only have 3 variables. So just look at the pretty picture over here, ignore the code. Here is the data set I have. So this is a scatter plot. Each point on the plot represents a different power plant. And you can see on the horizontal axis, this is the amount of energy that the power plants are producing. Some are producing just a little, some are producing a lot. On the vertical axis is the amount of CO2 that the power plants are releasing. So you can see this power plant over here, it produces, oh, you might not be able to see my cursor. Can you see my cursor?
Yes, we can see it.
Okay, great. Well, this power plant over here, it produces, around 3 times 10 to the 7 kilowatt hours of energy, but it is generating maybe like 4 times as many emissions as this power plant that's producing the exact same thing. So this power plant, like maybe it's very poorly efficient, maybe it doesn't have carbon scrubbers. This one, let's say it has carbon scrubbers, it's a lot more efficient. So that's the data I'm going to work with. I'm now going to create some functions that we talked about. So the function that generated predictions and that measured the error. Don't worry about the code. Just wait till the pretty pictures show up on screen. Okay, so I'm now going to train my algorithm using this optimization function. So at the start, I just randomly got some parameters. So randomly picked these values over here. And then after that, I started using my algorithm to predict different parameter values. You can see the error of the algorithm changing over time. So at first, the error was very high. And you can see like it's spiking up and down randomly because I'm just generating random equations, At first, the error is going up. But then you can see the AI algorithm picked a set of parameters. It picked some numbers that worked a lot better, and you can see the error fell a lot suddenly. Then again, it started picking random parameter combinations. It picked some bad ones so that the error increased again, but then again, it got lucky. The error suddenly dropped. Because this algorithm is based on randomness, I could in fact run the algorithm again. And now the algorithm, it starts with some new parameters. you can see it immediately gets very lucky and then not so lucky, not so lucky, then gets lucky again at the end. Every time I do this, a new graph will pop up because of this algorithm being based on randomness. Now, there are other optimization algorithms, just like there are other error functions in AI. I just chose the simplest ones to show you because this one is just trial and error. This one you can see sometimes, the algorithm, it will run for a very long time, and you can see over here the error is slightly going up. So this is one of the downsides of the algorithm. There are other AI algorithms that are based on calculus, which I don't have time to teach you in an hour, where that problem wouldn't occur. So this is what working on AI is like, you have a bunch of different choices of math equations to use for your uh, predictions, for your error functions, for your optimization algorithms. And based on the ones that you use, sometimes you get better results, sometimes you get worse results, sometimes you get faster performance, sometimes you get less. And that's what, you know, AI scientists, that's what they go around doing all day, changing these equations, selecting the best ones, experimenting to figure out how do we get the error to go as low as possible so that we can use these AI algorithms to give us results that we want. In this case, to help us plan whether this new power plant is going to comply with the regulations for the environment. One last thing, I just want to show you the parameters that the AI algorithm picked. Let me print those over here. So the numbers that it picked were things like 74.955 or negative 65.902. Very different from like my choices of 3, 4, 5, 6, as you can see. So it's not very intuitive, how these AI algorithms work under the hood. So it takes a lot of effort to try and figure out and reason about how these things are working. How do we make them work better? Because we can't write, the code that I have put up here. I can't write a for loop or I can't write whatever. I can't write code that I can reason through as a human to figure out what is the AI algorithm doing under the hood. So these are some of the challenges that AI, scientists, they will try and work on to try and grapple with. If you have any questions for me, iteration is like in this, someone answered it, so it's a repetition for a loop, but an iteration is every time we deleted these equations and then replaced them with a new set of equations. So every time we did that, that was an iteration of the algorithm. That was the algorithm getting better. Any other questions for me? All right. Well, if not, that is the lesson for today.